Okay, and welcome to Newton's Law of Universal Gravitation, which means that we are slowly delving into some space science, which is fun, because the last time you guys would have seen anything to do with space would have been back in grade 9. So Newton's Law of Universal Gravitation is actually an example of Newton's third law, and it just talks about how two objects exert gravitational forces of equal magnitude but opposite direction of each other. And if you did that forum post with the simulation, that would definitely help your understanding right here. And the important part here is that this magnitude does not depend on the medium. And when I say it doesn't depend on the medium, that means it doesn't depend on if it's space, air, or water. They exert the magnitude that they are exerting. And that force formula that we're going to use is now Fg is equal to G M A M B over R squared, where G is equal to our gravitational constant of 6.67 times 10 to the negative 11 Newton meters squared divided by kilograms squared. And then MA and MB are the masses of the objects, and the next one that I want to define for you is R, which is not the radius, but instead the distance between the centers. So what we're going to do here is we're going to apply our formula to an example here. We are given a mountain, we are given a height, we're given a body, and we want to find the difference in the magnitude of the weight, so the difference of the Fg, which is the same thing as saying Fg2 minus Fg1. So the base of the mountain in relation to the Earth, so the R of the Earth, is 6.38 times 10 to the 6, forgot my 8, meters. And then to the top of the mountain, remember this is the base, our top, is equal to 6.38 times 10 to the 6 plus 5959 meters. So then if I want to find the force of gravity at the top of the mountain and the base of the mountain, let's set this up. We have Fg B, which is equal to the gravitational constant, the mass of the person, mass of the Earth, over RB squared, which is equal to 6.67 times 10 to the negative 11 Newton meters squared. That's a lowercase m, kilograms squared, multiplied by our person, which is 55 kilograms, multiplied by the mass of the Earth. And you can see how this formula is kind of working together right now. 4 kilograms, because then these kilograms cancel out already, which is awesome. And then it's divided by RB squared, so we're going to cancel out these meters squared here right away. Because it's going to be squared. So that gives us a resounding 538.04 newtons, which everything, we have 4 sig figs here, 3, 3, 3. We got to get that to 3 sig figs, so you can keep that as 538 newtons. Oh, that's a different example I have going on there. Perfect. And then we need to calculate the Fg at the top of the mountain. So I'll write a little bit smaller, and I will move this a little bit up. So then when we are looking at our Fg at the top, same setup, G, M, P, m Earth over RT squared. So you can kind of see where a difference might occur here. The gravitational constant is the same. It's this guy right here that's going to give us a difference. So keep an eye on that. 6.67 times 10 to the negative 11 Newton meters squared divided by kilograms squared. Mass of the person stays the same. Mass of the Earth stays the same. And then our RT looks a little different now because it's 6.38 times 10 to the 6 plus 5959 meters squared to give us a resounding 537 newtons. So this difference of the magnitude, this FG, delta FG, is going to be 1.00 newtons. The other thing that we can do with this is we can use proportionalities actually to discuss and solve things. And this is like how we deal with the separation distance in masses and how they change. So you can see in this one, the MB in the first situation is a lot more. The MA in the after situation is a lot more. So we are going to try to figure out some stuff that we have here. And what we're going to relate this to is our force of gravity and how it relates to the masses and how it relates to the radiuses. So we want to figure out this FG. We know FG is usually the gravitational constant in the masses and the radius, but what we want to find first is just deal with the masses. So this is FG in relation to the masses. So that we use this proportionality sign. Now, if I look from here to here, and then I look from here to here, we can kind of see how those differences are coming into play here. So I want you guys to take a good look and figure out what you're kind of seeing there. We have our FGs, we have a radius, we have an FG for our original situation, but we want to figure out what the FG is for the secondary situation. So then in the question, it says that we need to determine the magnitude if the separation distance is halved. So this is halved. MA is increased by 6 times and MB is halved. So that's what I was going to go check. I realized that I did not include all of the values that I should have. That's fine. We make adjustments. So our FG is equal to 6 MA, or proportional to, sorry, and 1/2 MB. So then this gives us the proportionality of 3 MA MB. And we also have the FG in relation to the distance and how that is proportional. So this is halved. So we have 2R squared, which means that it is proportional to 1/4 R squared. So the factor change of FG is going to be these guys together. So 3 1/4. So factor change. Which gives us 3/4. And then to calculate FG from here to here, it's just multiplying it by 3/4. So 3/4 just like that. So if you are curious on how to do something like that, I know there's a practice problem in the book and there's also one in your assignment. So if you are having issues, ask away, but you're just going to set up the FG in proportionality to the masses first, then the distance, then you're going to relate that factor change together and multiply it by the FG. Next, we have a question. It says, during a lunar eclipse, the Earth, the Moon, and the Sun are aligned on the same plane as shown in this figure. Yes. Using some data, calculate the net gravitational force exerted by both the Moon and the Sun on the Earth. And we have the data here. Earth, mass of Moon, mass of Sun, RE to Moon, RE to Sun. So I want to find the net gravitational force on the Earth, so I need a free body diagram, which is we have Earth, Moon, Sun, so FG1, FG2, Moon and Sun for short. And then we're going to try and find this F net. Now we can tell because the mass is so much larger for the Sun that our F net is probably going to be pulling in this direction. And that's just dealing with the magnitude of those things. So the first thing that we need to do is we need to set up our first part of the equation here. So I want to calculate the FG exerted on the Moon, by the Moon on Earth. So Moon on Earth. This gives us G, M, Earth, M, Moon, all over RE to Moon. So that's just to remind you that you're trying to find like the distance between the centers of Earth and the Moon. Okay, our gravitational constant stays the same. Multiplied by the mass of the Earth and the mass of the Moon. All over RE to M squared. Plug that all into your calculator. 3 sig figs, 1.99 times 10 to the 20 newtons. That is towards Earth's center here. Okay, then we're going to do the same thing. FG, which is equal to G, M, Earth, M, Sun, all over RE to Sun squared. Everything's going to stay pretty much the same except for the last one. All over 1.50 times 10 to the 11, which to 3 sig figs plugged into your calculator gives you 3.52 times 10 to the 22 newtons towards Sun center. And then the net gravitational force, so FG net is equal to the FG 1 and 2 added together. Then when we looked at this situation above here in the force diagram, our FG1 is going to be negative and our FG2 is going to be positive. That's just because it's left and right. So then this is going to give you negative 1.98. That was weird. 85 times 10 to the 20 newtons plus 3.52. I got some extra values here. times 10 to the 22 newtons, which gives us, if we plug that in, 3.50 times 10 to the 22 newtons. So it's pulling more towards the sun, like we said. At this point, I would suggest pausing the video, going to do some questions, because the next thing that we're talking about is the next day stuff. I just want to do it in all-in-one video, and it's about the Earth and the tides. This is a heavy reading one, so feel free to like speed this up or slow this down, whatever is going to be better for you to understand and to get through the video. So Newton used the concept of gravity to account for Earth's tides. And this is something that we talk about a lot in terms of grade 9 science and younger science, just tides in general. But there's tons of other factors that affect the tides, like coastline, topography, the ocean floor, friction, and the Earth's position around the sun, its rotation, seasons, everything. So the moon's influence on the tides is actually pretty large. Some people don't think so, and they think like, oh, the moon has nothing to do with it. But the moon's force of gravity pulls on Earth's landmass, and it's actually part of the reason why Earth is not a perfect sphere. We'll get into that. At the same time, the Earth rotates on its axis. It allows different parts of the Earth to rotate in and out of the high tide and low tide. And you'll see that in the next one here. But it's like, because of the rotation and how the gravity force of the moon pulls on the Earth influences the high tide and the low tide. So when we look at this diagram below here, these are the high tides that's happening, the A and B. And that makes sense just looking at the diagram, because it is pulling towards the moon. These guys are going to be a little bit less because they're not directly there. The bulge in the ocean at A is because the ocean is closer to the moon. Therefore, the opposite is true for B. The ocean floor experiences a larger force of gravity and therefore is pulled closer to the moon than the ocean. Now, between the bulges are the low tides. So anything that is happening in here, this is in between, this is low tide stuff. And that's because it's rushing towards that high tide. Now, since the Earth rotates on its axis every 24 hours, the bulges don't move necessarily, but the Earth rotates underneath of it. So that point that is at low tide and high tide, they kind of like are going to move in relation to each other. But the thing is the Earth is moving, the moon is moving, the Earth is rotating. So a high tide is replaced every six-ish hours. Now, that's not necessarily always true in that it doesn't occur every 6 hours. It's like saying that the Earth has 365 days. It's not necessarily true. The time intervals are a little longer because of all the different rotations and because of the moon also revolving around. Because that happens once every 27 days, and the moon is influencing where the bulges are because of the gravitational force. So it's actually just like a teeny bit longer than 6 hours. And it's the same thing as like when we have to calculate in the fact that we really have 365.4 days in a year. I think it is, or 365.4. It's really awkward. There's like an extra quarter of a day that we need to account for, which is kind of why we have leap years. Now, since the Earth's axis of rotation is tilted, the two high tides are not equally high, and the same thing for low tides. In most places on Earth, the difference between high tides and low tides is about a meter, but the largest difference is about 17 meters and actually occurs in our very own Bay of Fundy in Nova Scotia. This is partly due to the tilt of the Earth's axis, but as mentioned previously, other factors influence this case as well. The shape and the size of the bay in particular are pivotal factors, and if you're interested in that, there's 100% a forum video that you should go watch and go check out, and you should just also, if you're not in my class, go Google the Bay of Fundy stuff. It's super, super cool, and I've never got to see it, but I've heard amazing things about it. Also, the other thing that we can briefly talk about is the interplanetary travel stuff that occurs. If you watch the movie The Martian, that gravity assist movement was not just for science fiction. Scientists who plan space missions have to use that gravitational force, and all of those planets like change the speed and the direction. So you have to like calculate the position and velocity of all of these different celestial bodies many years in advance. So it just helps kind of assist in I couldn't think of a better word, assist what that interplanetary device is trying to do. If you haven't watched The Martian, it's absolutely a great example of it though. And if you're interested in more space science stuff, because we're in Saskatchewan here, you should definitely check out the U of R and the U of S stuff, and you can see all of these different ways, like our Voyager, how it had to like pass close to Io, Ganymede, and Callisto, and how it like redirected it and changed its direction. So keep an eye on that. If you have any questions, please let me know. I know this one was more of like a reading one, but I hope you enjoyed it, and good luck.